Let's talk about Lagrange's theorem. So let G be a group, H be a subgroup. Given an element little a in G, we defined a subset A times capital H. It consists of all elements of G of the form little a times little h, where little h varies over capital H. Such a subset is called a left coset of H in G. And I'm going to use the notation G mod H down here to denote the set of all left cosets of H in G. So to give a quick example again, if G is order 6 generated by a single element A, so it's a cyclic group of order 6, so it has 6 things, E, A to the 5, and A to the 6 is again identity, and H is the subgroup generated by A cubed, which has 2 things, identity and A cubed, then this set has 3 things. Here is a coset, here is another coset, and here is another coset. Okay. These 3. All right. G colon H just means the size of this set G mod H. So that's the number of left cosets. In this example, it's 3. It's called the index of H in G. All right, we had this 7 equivalent conditions, this lemma. You gave 7 equivalent conditions telling us when 2 elements are in the same coset, 2 elements A and B. So all these 7 conditions are equivalent to saying A and B are in the same coset. And when that happens, we wrote A congruent to B mod H. So that is a definition really, so maybe I shouldn't call it a lemma anymore, but these 9 sentences carry exactly the same information. And what follows from this is that this congruence is an equivalence relation. So it follows that if you call R to be the all ordered pairs in G such that A is congruent to B mod H, this is an equivalence relation on G, and the equivalence classes are the left cosets of H in G. And this immediately implies the first part of Lagrange's theorem, which I have written down here. Let G be a group and let H be a subgroup. Then the left cosets of H on G form a partition of G. Because whenever you have an equivalence relation, the equivalence classes form a partition of the set. This we know. So we have proved part A. Part A gets some counting consequence out of this when G is finite. So when G is finite, so assume G finite, so then H is finite as well. So let's at least assume H finite right now. Then I claim that H and AH, and take some A in G, that these 2 sets are always in bijection. They have the same size. In fact, I can write down a bijection. This left multiplication by A is a bijection, where this map was introduced while proving Cayley's theorem. This is a map from G to G, which is a bijection, but just restricted to H. What does it do? It takes an element and multiplies on the left by A. So if you take something from H and multiply on the left by A, you get something in AH. And I claim this is a bijection because I can write down the inverse. The inverse is, in fact, the inverse of this map is just left multiplication by A inverse. The inverse of this map is just left multiplication by A inverse. Just verify this. I won't write a proof. There's hardly anything to write. So by definition, it takes you from H to AH, and you know that this is the inverse of that. So it's a bijection. So the size of H is the same as the size of AH. Like you see here, all of them have size 2. When you multiply by A, you go from this set to that set. When you multiply by A inverse, you go back. That's the bijection I'm talking about. So any two left cosets of H in G have the same size. Because two left cosets look like this, AH, BH, but both of them have the same size as the size of H, so they have the same size. And now that gives me this conclusion, because let's now count how many things there are in G. So assume, so this is proof of B, if you wish. Assume that G is finite, then the size of G is the sum of the sizes of the cosets by part A. Because you have this group, it's partitioned into these cosets, etc. And I can count how many things there are by counting how many things are there in the first part, how many things there are in the second part, and adding them up. But then here we see on the right that each part has the same number of things, this many. So this is same as the size of one coset times the number of cosets. And by a coset, I mean a coset of H in G, right? But the size of one coset is the size of the subgroup, and the number of cosets is what I'm calling the index, absolute value of G mod H. And that tells me this master formula, the size of G is equal to the size of H times the size of G mod H. In particular, the size of the subgroup and the number of cosets, both of them have to divide the size of the group. Like in our silly example, the size of the subgroup is 2 and the number of cosets is 3. And 2 times 3 is 6. And this puts a strong restriction on what kind of subgroup a group might have. Okay? So for example, a group of prime order must be cyclic, because there is no proper factor, so there is no proper subgroup. So if you take any element, it has to generate the whole group. So that forces that if the only group of order P prime, then only group of order P up to iso is Z mod P. This sort of corollary is immediate because there is no subgroup. And by the way, there is a similar statement that holds for the right cosets. And if you write H backslash G as the set of right cosets, then it follows that the number of right cosets times the size of the subgroup is again size of G. So in particular, you get this corollary that the number of right cosets is same as the number of left cosets. The left cosets and the right cosets could be different, but they are the same number of them. There's a lot more corollary to go through, but maybe I'll just talk about two of them, which are elementary statements from arithmetic due to big names. The first is the theorem of Euler, and proving them just by arithmetic is some work, but it just falls off, we'll see, from the group theory. So this says, so I need a little notation. I'll write phi n to be the size of the group Z mod n star. Remember, Z mod n star means the multiplicative group of all k in Z mod n such that they're relatively prime to n. Yeah. So like Z mod 12 star has 1 and 5 and 7 and 11. And this number is called 4 is phi 12, etc. So phi of 7, for example, is 6 because there are all 6 numbers below 7 are relatively prime to 7. Now Euler's theorem says let n be an integer natural number, a be a integer, and they're relatively prime, the GCD is 1, then a to the this number, by the way, this is called Euler totient function. It's a rather important function in normal theory, is congruent to 1 mod n. A to the phi n is 1 mod n. And the proof is sort of really quick now. So notice that A is relatively prime to n, so it determines an element of z mod n star. The multiplicative group of numbers modulo n that are relatively prime to n. And the order of, let's call this thing G. The order of this element is the same as the order of the cyclic group that it generates, almost by definition. And that divides by Lagrange the order of the group. So this is by Lagrange. The order of a subgroup divides the order of the group. But this number is what we are calling phi n. So that tells you that the order of this element is a factor of phi n. So if I raise this guy to the power phi n, I get the identity. And the identity of this group is 1. So this equation holds in z mod n star. But if you translate it back into z, this reads a to the phi n is congruent to 1 mod n. The equality in z mod n translates to that. Yeah, so things like you can calculate phi of 100 is 40. So if you take some number relatively prime to 100, I don't know, 39, then I get that 39 to the 40 is congruent to 1 mod 100. So I've calculated the last 2 digits of 39 to the power 40. It starts like something something and then 0, 1. That sort of thing. There's a corollary that is ascribed to Fermat. This came first, actually, an Euler generalized Fermat's theorem. A is an integer, P is a prime. Then A to the P minus 1 is congruent to 1 mod P. And this follows immediately from Euler. With n equals p, you notice that z mod p star is all the numbers below p from 1. So its size is p minus 1. There's a general formula for calculating the Euler function, actually, so from which I proved this. You can look it up. Yeah, so this can be calculated rather easily. But you get things like, I don't know, 43 is a prime, so 43 minus 1 is 42. Take any number that is relatively prime to 43. 77. So you get that sort of thing. Yeah, they have a lot of number theoretic consequences. We could go on, but at some point one has to stop. I guess we'll just stop here.